Good morning. So when I give a physics lecture, it's interesting. We love the physics lectures where we have the ability to demonstrate all the physics we know. And you've already gotten that this morning. Sound, light, maybe not water, and a lot of electricity, computing, screens. I'm going to talk about gravity a little bit and try to aim it at this themes of this meeting, more or less to illustrate what physics is and how we move forward in physics within the concept maybe of how it all began is what I'll try to get to by the end. But one of the themes that I think this section is what's the point? For physics, that's simple, doing the kind of physics I do. It's much more complex for most of this meeting, but for physics, it's simple. We just try to satisfy our curiosity. As kids, curiosity is what drives us, and when we get to be adults, most of us do other things. Some of us still act like kids and try to satisfy our curiosity. So everything I do has to do with curiosity. Remember that curiosity killed the cat. Anyway, this picture here is a picture of the Big Bang, and I'm going to come to that at the end because we have a television program called The Big Bang. We talk a lot about the Big Bang, but we don't understand it, and I'm going to try to give a hint why that's a burning question, at least for me, and how we might get at it. But I'll do that through talking about the studies of gravity first that I've done. So the story, human story at least, starts with Einstein. In 1915, Einstein made a new theory of gravity. We all grew up learning gravity through Sir Isaac Newton, who had a theory of gravity, which he called unified gravity. It described how the apple falls out of the tree to the earth. It described how the moon goes around the earth. It described how the earth goes around the sun. It described the tides. It described everything to do with gravity, basically, for more than 200 years, and was the most successful physics theory ever. He also introduced the scientific method, so Newton was pretty important. Einstein came along, and in 1915, he made a new theory of gravity. So why did we need a new theory of gravity at all, since we had a theory? It's a little bit the way physics works. We have a theory. There was nothing wrong with Newton's theory. It just didn't do the job. I'm not going to talk about this complicated formula, by the way. You learned a formula that was much simpler, that was Newton's formula. But Einstein came along and made a new theory of gravity. It's really complex and hard to understand, even for physicists. But it solves two problems that Newton had. Newton's theory that we all learned told us that when the apple falls out of the tree, the earth pulls it down. Or our teacher told us if we jump up, the earth pulls us down. And some of you, not me, might have asked your teacher why the earth pulls you down. Newton never explained that. Einstein does. So Einstein attacked the unanswered part of the question. What makes you attracted to the earth? What makes two bodies pull together? I'm not going to explain it. It's the warpage of space-time, these words that you hear, which are explained by this formula here. The second problem with Newton's theory, and the fancy physics words are instantaneous action at a distance. What does that mean? That means when the apple falls, you see it right away. Or, if the sun were to burn out right now, it takes 7 seconds for the light to get here, but you would know it from gravity immediately in Newton's theory. In Einstein's theory, the message comes at the same speed as light, the speed of light. So he solved those two questions, and then he introduced the possibility that there was something new. The first thing that was new is that light would curve. And there was a spectacular experiment done by looking at stars going behind the sun in 1919 and measured this curving of light around the sun. The reason it bends going around the sun is this warpage of space right around the sun that causes the turn. The second prediction of Einstein and it shows that burning questions might take us a long time, was in 1916, I think I have it. No. In 1916, he predicted there was something called gravitational waves. That's waves, just like electromagnetic waves that made all the light and sound and so forth you just heard. And 100 years later, so it takes us a while, we saw gravitational waves. We saw them from something called black holes. A black hole, I'm not going to describe mathematically. It's a difficult mathematical concept. But conceptually, what it is a region of space that has so much gravity that nothing can get out. Not even light, because light bends, remember. So everything is trapped, therefore it's black. So this is a black hole. They come about from a star, a heavy star that collapses after it burns up all its fuel and makes a final, very dense amount of matter. Our sun is too small to do that, but a heavier star can make a black hole. So we saw two black holes that are going around each other, just like the moon around the Earth, going around each other. But by Einstein's theory, as they go around each other, they accelerate and lose a little bit of energy. That goes into gravitational waves. And eventually, because they lost energy, they spiral into each other. I'll show you that in just a minute. But first, the distances. So here's a picture of Puebla City and Mexico City. And here's the two black holes that we observed put on top of that. One of them is 36 times the mass of our sun. The other one is 29 times the mass of our sun, and they're only apart about the distance between Puebla and Mexico City, and they're going around each other at half the speed of light. That's what we observed. Each of these, by the way, to put it in reference, the black dots are 10 million times the mass of the Earth concentrated into this small space. So that's what makes it have such strong gravity. This is the recreation of the observation that we made 100 years after Einstein predicted of the merger of two black holes. They're going around each other. They're losing, from way out in the universe, they're losing energy and they come together. You'll note at the top, I say 1.3 billion years ago. That's how far away this was in the universe, and it was traveling all this time. By the time it got to us, we could detect it. This is then the gravitational waves going out, and they cause, and that's what we detect, that space gets warped. Whatever it goes through or comes to gets warped. So here it comes toward the Earth, takes 1.3 billion years, and by the time it gets there, it warps the Earth. The amount I exaggerated a little bit in this picture, as you'll see. So it doesn't quite do that. We're not able to measure it. It's much, much smaller, and we needed a special instrument to measure it, and that's what took so long. And the special instrument is shown here, which I won't talk about in detail because it's not the point today. These are the two instruments. They're large. They're 2.5 miles on a side, one of them in the state of Louisiana, the other in the state of Washington. Anyway, that was the observation of gravitational waves. This is the signal. I'm not going to explain the signal, but it's basically getting bigger. And that's as the waves merge. This is about 0.2 of a second when we observed it. These are the two different laboratories, and they saw exactly the same thing, separated by 7 milliseconds, which told us where it was coming from. So that was the discovery. I went just a couple days ago, before coming here, to consult with Mr. Einstein in Bern, Switzerland, where I flew directly from there with a night's sleep here to ask him what I should talk about. And after, as a result of this, in terms of the burning questions, we disagreed, so we didn't do that. So instead, I'll talk about what I think is a burning question as we go on. So first, to illustrate why science, as it develops, gives you the ability to do something else. So we did something, we got awarded for it, but this gives us the ability to move another step somewhere. This is very much in the case of gravitational waves like Galileo in 1608. He looked through a telescope in 1608 for the first time. They'd made lenses for glasses. He looked through a telescope. He looked at Jupiter. He saw Jupiter had 4 moons. That told us a lot about the fact that planets go around something central like the sun, so it had a lot of implications. And it was the beginning of astronomy, the first time that anybody looked at the sky with something other than our eyes. And astronomy's gone a long way since then. We now, for the first time, have looked at the sky through gravity instead of through light or electromagnetic waves. And again, there's many opportunities for what can be done. So the question is, what can you do? We already did something in the last year, and that's shown here. There's another funny, very difficult to understand object when you don't make a black hole and a star collapses, called a neutron star. It's smaller than a black hole, but very dense, and I show a picture of it here. It's only about 20 kilometers across and weighs about 1.5 times the mass of our sun. And we know about them through radio telescopes, and they're called radio pulsars. And the reason they give you a signal regularly is it looks like a lighthouse. As the star spins around, it's moving in different direction. As you see it as a signal. It's the most constant signal that we have in the sky. And it's a clock, basically. So it's a new kind of clock. We saw 2 of these objects going around each other and coming together. Something that wasn't the initial discovery, and a lot of astronomy, which I can't talk about in 5 minutes, we did with that. This is what I was going to talk about, because it's a serendipitous discovery, if you want. And when you talk about burning questions and what you're doing, we weren't looking for this result. It turns out that when we look and try to understand how the Earth was put together, we have a hard time explaining where the heavy elements came from. In fact, we can't. So why is it that we can dig into the Earth and in a mine and find gold or platinum for your rings? We try to explain that, because physicists always do, by the fact that when a star does collapse, maybe there's some new nuclear physics mechanisms that create that. It never was very satisfying. But the observation of these 2 neutron stars coming together is very much the way, which we observed for the first time, the way that we create these heavy particles that we see in the mines, but also create in the periodic table, in the laboratory. In the laboratory, they're made by bombarding neutrons on some heavy element, and then it makes yet a heavier one. So this is an analysis of what we saw, and the yellow parts, or gold parts, are for each element, how much of it was made by seeing the phenomenon of neutron stars coming together to make the heavy elements. And you can see I've circled gold and silver, and in that case, basically, they were made by this kind of, we think now, that's the best argument we have, by this kind of argument. So, without it being it was a burning question for somebody else, but serendipitously we discovered it. What do we think we might do that's really a burning question? As you can see, sometimes our burning questions take hundreds of years to answer in physics. So this is my answer, not Einstein's, and it really has to do with the Big Bang. The Big Bang is how it all began, presumably. And in the Big Bang, we have a problem of understanding, of course, our curiosity of how it all started and how it evolved into having planets and stars and galaxies and so forth. But there's a basic unanswered question, which is why we're here, basically. And that is, if I go into a physics laboratory and I make a lot of energy, E equals mc squared, that's the Big Bang itself, it creates as much matter as antimatter. So where is the antimatter? In fact, by everything we understand in physics, all the matter and antimatter should have annihilated, and just be energy, not be matter. So there wouldn't be us here, or matter, if there wasn't a mechanism that we don't understand yet that created matter more prolifically than antimatter. And we don't know the answer to that, but the tool to get the answer is likely to be gravitational waves. And I show that in my last picture here. Here's now, and everything we know about the Big Bang comes from telescopes and electromagnetic radiation and photons, but it only goes back to 100,000 years after the Big Bang itself. We can't penetrate further than that because the photons got absorbed. To go earlier, the best possible way is gravitational waves. The fact that we couldn't detect them for 100 years, they're not absorbed very easily, they don't do very much, but it means, in principle, we have the ability to go back to the very early instance of the Big Bang and understand what happened. Do we know how to do that now? No, but we have the possible tool, and that's my burning question. Einstein had a different answer, but that's it. Thank you.
Bravo, bravo.